Okay, picking up where I left off. Converging lens. A converging lens is a convex lens with a positive focal length. That's what this plus sign up here means. So if I have rays that are incoming from the left, and I'm going to say these rays are parallel to the optical axis. Just to simplify the sketch here, I'm going to indicate that all the refraction happens along the lens plane, although in practice we know it happens on both edges, when it enters and when it exits. But since we're using the thin lens approximation, we can represent the refraction as taking place on the lens plane. Okay, so these rays are all going to bend and focus at a particular point, and this particular point right here would end up being a real image. The distance is f, the focal length. So f, which was calculated from the lens maker's equation right here. In practice, all we need is the focal length f. It tells us how far from the lens plane parallel rays focus. Okay, that's a converging lens. It causes parallel rays from a source that is infinitely far away. For instance, the rays of the sun, technically they're diverging, but the sun is so far away that the rays appear to be parallel. So a converging lens will cause those rays to focus at a point and produce a really hot spot, right? Or concentrate all that light energy to a single spot, and you could start a fire. All right, now diverging lens is just going to be the exact opposite. So diverging lens turns out to have a negative focal length. And once again, just to center it on the picture, I can represent a lens plane and an optical axis. And my diverging lens actually appears to be concave. Now, actually, if you look at the lens maker equation here, there's many ways to get a diverging lens. For instance, you could have one side that's convex and one side that's concave, and it could still be a diverging lens. It would just depend on the relative size of R1 and R2, right? And then which direction the light is coming, from the right or from the left. Okay, so let's say that I have parallel rays that are incoming from the left. These rays are going to diverge. And if I draw a dotted line backwards, they diverge as if they're diverging through a point right here. And I could trace this for all of the rays. This dotted line represents what's called a virtual ray. It doesn't actually exist, but it appears it's just connecting the real ray backwards in a straight line. And these rays that are diverging right here, they all appear to be diverging from this point right here, which would be a point of what we'd call a virtual image. So a diverging ray in sunlight, for example, wouldn't produce a bright spot, but it would produce a virtual bright spot, which basically just means you could see that bright spot if you looked through the lens from this direction. So if I was looking through in this direction, this is a little eye. Looking through this direction, I would see the rays as if they're diverging through from this point right here. Okay, so now let's actually look at image formation as it pertains to converging and diverging lenses. And one of the things we're going to use is what's called the thin lens equation. Now it turns out the thin lens equation is, again, just an application of Snell's law and only valid for approximation for thin lenses. Well, for thin lenses, where the lens is very, very small compared to the object distance, and the lens is really big compared to the wavelength of the light, so we can treat it as rays. So the lens equation says 1 over f equals 1 over s plus 1 over s prime. And I will describe what that means here. So I'm going to start with a converging lens. Here's my optical axis. Here's my lens plane. Here's my converging lens. And let's say my converging lens, here's the focal point. Now, a converging lens, just like a diverging lens, will have a focal point on both sides. Let's say I have some object. And this object right here, it's a little tree, object O. And the object is a luminous source, meaning it's reflecting light rays in all directions. Okay, now some of the important distances here would be, first of all, well, where the object is located with respect to the lens plane. So this distance right here I call S. It's the object distance. Now, this tree is luminous, so it's either reflecting light in all directions, or it's transmitting light in all directions. And there's an infinite number of rays that actually pass through this lens, but we're going to focus on a set of rays called principal rays. Okay, and principal rays, I like to always look back to converging and diverging lens, their basic properties, to try to figure out what those principal rays are. Well, one ray we know of to begin with is simply the ray that's parallel. I'm going to pick a point just at the top of the tree. I'm just going to look at the light ray that comes out of the top of the tree and trace that. And then every other point will be something similar to that, right? So this is a technique we call ray tracing. Okay, so if I have a light ray from the top of the tree that's parallel to the optical axis, when it encounters the lens, it's going to move through the focus point. That would be one of my principal rays. Another one of my principal rays would be the ray that goes directly through the center of the lens. Now, it turns out that this ray is not refracted at all in the thin lens approximation. So this ray would be straight like this. Okay, now the final ray, which I could draw here, is a ray that comes through the focus point, and then it emerges parallel. And you might wonder, how do I know this is a principal ray? Well, light rays are actually reversible. So just imagine the arrow is going this way. A ray that comes over here would go through the focus point, and you might say, well, that ray doesn't even go through the lens. How is it going to bend if the lens ends right here? Well, again, we're using a technique called ray tracing just to figure out where the image is going to focus. even though one of these principal rays doesn't actually go through the lens, it still allows us to determine that. All right, so let me correct my picture here a little bit. Now, if I drew it perfectly, it would look something like this. All these rays focus at this point right here. And this is my image. And the image in this case, it's a real image, which I could take a picture of, say, by projecting it onto a screen. So the distance I call S prime, and that's the distance from the lens plane to the image. And in this case, I have S, S prime, and F all positive. All right. Now, the thin lens equation right here relates S, S prime, and F. So if you know the focal length, let's say you know the focal length of your lens and you know where your object is located, you can determine where the image is. Let's say it's an unknown lens and you want to determine its focal length. You just put an object at a certain distance, measure where it's focused, and you can determine F. Okay. Now, one other property here for lenses, and that's called magnification, because you'll notice here that the image, just as I've drawn it here, is not the same size as the object. So let's say the object initially has a height of h, and then the image has a height of h prime. So we define the magnification m to be h prime over h, which equals negative s prime over s. This last relation here comes from properties of thin lens and application of the thin lens equation. All right, and some simple geometry which you can construct with these triangles here, similar triangles. Okay, so other rays do exist, but we just don't sketch them. The image is formed not by simply the principal rays, but a whole range of rays that go through the lens, an infinite number. But the principal rays are the ones that are easy to draw, which allow us to determine where the image is, and that's why we draw them and not others. Okay, now notice that the image forms regardless of how much of the lens is actually displayed. So for instance, I could put a block here. I could block out half of the lens, and still a range of rays at the top are still going to focus to produce the image. Since less light energy is getting through, however, that'll just mean that the image is not quite as bright, but the ray will still be there. Okay, so let's look at another example. I'm going to use the same lens. Okay, but this time, I'll make the focal length a little bit smaller. How about that? Smaller focal length. But this time, I'm going to put the object inside. Here's my object inside the focal length. Well, in this case, what we have is, let's try to figure out where the image is going to be produced. So here's my S. I'm going to draw the principal rays. I have one ray that goes like this, parallel, right, and then through the focal point. I have another ray that goes right through the center, undeflected, and then I have a final ray one that goes way up here like this, and emerges parallel. Now notice that this doesn't seem to be producing an image anywhere, but if I took my eye and I look through the lens in this direction, all of these rays that I see would appear to be diverging from a common source back here somewhere. So I can trace those rays backwards. And they all appear to be diverging from a common source. So here's my, if this is my object, here is my image. And the distance S prime in this case is less than 0 because the image is on the same side as the object. That's one of the properties of the thin lens equation. Now this image is a virtual image, meaning this image can't be projected, but one could see it if they look through the lens. From this direction, they look through the lens, they could see an image which is actually blown up, although that image doesn't actually exist. Okay, let's plug in a couple numbers here just to do some math. Let's say, just so you see practically how this works, let's say that you're given S equals 5 centimeters and F equals 8 centimeters. And the question is, find the image location. Is it real or virtual? And what's the magnification? Well, just by drawing the principal rays, we've already determined it's a virtual image. So let's determine where that object is located. So I'm going to solve for 1 over S prime is equal to 1 over F minus 1 over S. So this is equal to 1 over 8 centimeters minus 1 over 5 centimeters. Right, and if you're good with fractions, you'll see that the lowest common denominator is 40. So I have 5 over 40 minus 8 over 40, which gives me minus 3 over 40. In other words, S prime is equal to negative 40 over 3, or negative 13.3 centimeters. So I do get a negative S prime. The negative S prime corresponds to a virtual image on the left, the same side as the object. Now, if I was to calculate the magnification I can do pretty simply. The magnification M is equal to negative S prime over S. And S prime is negative 13.3, and S is 5. So I get a magnification of, and there's an extra minus sign, which makes it a positive there. So I get a magnification of 2.67. So this image is upright. Positive magnification, it's an upright image. It's a virtual image, right? Because it's not real, you can't project it, but it's upright, meaning it's point orientated in the same direction as the object. All right. Well, let's continue on here and see what else we can learn about lenses. I'm going to try for a moment here to look at a diverging lens. Okay, so I'm going to create a diverging lens as follows. Here is my optical axis. Here is my lens plane. And here is my diverging lens. with a focal length less than 0. Again, there's going to be a focal point on each side. Let me put it out here, make it a little bit larger. F, F. And let's say I have an object on this diverging lens out here. So here's my object. And the object has a distance s. Now I want to figure out where is the image produced, and using ray tracing by identifying my principal rays, and is that image real or virtual? Well, let's just try to draw some of the principal rays. Well, one of the principal rays that I can draw is simply the ray that goes directly through the center of the lens. And now I'm wishing I had a ruler on hand. So I'm going to have to try to freehand this again. See if I can do this. So all right, I get a ray that looks like this. Okay, now what would be another ray that I have? Well, let's say I have a ray that is parallel to the optical axis. That ray would diverge along a line that goes through, when extended backwards, virtually through the focal point. So I'd get something that looks like this. And finally, let's say I have a ray that would head directly into the focal point. Let's say this ray was heading directly into the focal point, but I'm going to extend it virtually on this side, like that. And then I'm going to sketch a parallel line here. And I'm going to put arrows like this. Okay, now imagine I just reverse the direction of these arrows. What you would find is the light comes like this and diverges on a line that goes to the focal point. So this is one of our principal rays. It's just the arrows are going the opposite direction, but rays can travel in both directions. They're omnidirectional. Okay, now let's extend these rays backwards in space. And if I do that, I get this point right here where the rays all focus. So this is my image. And again, it is a virtual image, which can only be seen if you were an eye over here looking through the lens. Since S prime is on the same side as S, S prime is negative, but F is also negative as well. Okay. So here's our example of another lens. Now, or sorry, I should say a diverging lens. And let's try some numbers here just to put this into practice. Let's say I'll choose similar as the last example that we did, but this time I'm going to choose, let's say that the focal length is -5 centimeters and the object distance is 8 centimeters. Object distance, by the way, is always positive. It's only the image distance that can be positive or negative depending on which side of the lens the image appears. If it's opposite side of the object, then it is positive. If it's the same side, it's negative. All right, so what we want to try to figure out here is the image distance and and the magnification. So I'm going to use the thin lens equation. Solving for 1 over s prime, I get 1 over f minus 1 over s. So this equals 1 over negative 5 centimeters minus 1 over 8 centimeters. So now this is common denominator of 40 again, but I have negative 8 minus 5, which is negative 13. So s prime is equal to negative 40 over 13, which is equal to 3.08 centimeters. The negative makes sense, right? Because the image is on the same side as the object. And we verified that with our principal ray diagram here. And what about the magnification? Negative s prime over s. So negative 3.08 divided by s, which is 8. I get 0.385 for my magnification, which means I could calculate my h prime. H prime is just going to equal 0.385 times whatever the h is. Okay, so this is my h, and this is my h prime. So when you have a magnification that's less than 1, it's a reduction in size. So you can use a diverging lens in order to shrink the size of an object. A converging lens you can use to magnify an object or make it larger. Here we had a magnification of 2.67. Okay, finally what I want to talk about is two lens systems. Okay, a two lens system. Now you might be wondering, why in the world would you want to use two lenses in your system? Isn't one lens complicated enough for our ray diagram? Well, let me answer that question. And let me answer it the following way here. Let's say that, first of all, I have a diverging lens. And then over here, I have a converging lens. And right here, I have an object. Okay, now I'm going to put some numbers on this. And we're going to try to solve a simple problem here. So this one, I'm going to call this lens number 2, has a focal length of plus 20 centimeters. And this one over here, F1, has a focal length of negative 15 centimeters. And let's say that the object has a distance of 10 centimeters from the first lens. Let's say that both lenses are separated by 20 centimeters. Okay, so the question is going to be, given these two lenses, where is the location and size of the final image? So what is the location and size of final image? All right, now getting back to the question why we would have multiple lenses in a system. Well, optical instruments are built with multiple lenses in order to improve image quality. For example, a camera uses multiple lenses in order to correct for spherical and chromatic aberrations. A spherical aberration is one of the aberrations we already discussed that has to do with the fact that spheres don't perfectly focus light rays, but they do focus them well when we use the thin lens approximation. Sometimes that's called the paraxial approximation. That is to say, we take rays that are very close to the optical axis. And chromatic aberration has to do with the fact that the index of refraction is wavelength dependent. So materials, when I shine, let's say, sunlight through a lens or use a camera to take captured light, I have a range of different wavelengths, and there's a dispersion of the wave, which kind of causes a blurring of the colors. So this chromatic aberration can be corrected by adding multiple lenses. That's why the higher the quality of the camera, the more lenses that you'll use. Your eye, for example, is a lens or a camera, which allows you to take a picture when the rods and cones on the back of the retina are stimulated and transmit those light signals into electrical impulses, which are then transmitted by the optical nerve, and then your brain interprets that to form a picture, allows you to see. So that's a complicated process, but there's a camera there. All right, so other optical instruments might involve microscopes or telescopes, where you really want a crisp image, and the more even that second lens can really help you crispen up that image. Okay, so now that we've gotten that out of the way, let's then look to see how we might figure out where the final location and size of the image is going to be. Well, first of all, let's just ignore this lens over here. And what I'm going to do is extend the optical axis of this lens down. I'm going to draw the object. And I'm going to try to determine where the image is produced. So in order to do that, I got to do some ray tracing here. Now the first ray, which is, well, to draw some of the principal rays, let me first of all indicate, okay, if this is 10 centimeters and the focal length is 15, it's about right there where the focal point is for F1. F1 is somewhere, right around there. Okay, so on this side, that would put it somewhere around right there. So let's use that information then to try to sketch the principal rays for this first diverging lens. So this is a problem we can solve. It's actually very similar to this problem over here, except that the object is inside the focal length rather than outside. So, all right, so let's try to sketch some of these rays. Well, start out with the simple one, which would be the parallel ray. Right, the parallel ray is going to diverge through a line that goes through the focal point. Right? Then I have the ray that goes right through the center of the lens. That one doesn't do anything. And then I have the ray that is parallel on the other side of the lens. And goes like this. So then this ray diverges actually through this point. But if I trace it back, what I get is all these rays converging at a single point, and this is not the best picture here, but you can see it's somewhere in there that it converges. It might be hard to see on the camera picture here. All right, now I'm going to skip some of the mathematics here, and simply we can see here, this is S1 prime. This is S1. We already know S1 is 10 centimeters, and it turns out if you apply the thin lens equation, S1 prime is -6 centimeters. And the magnification that you get, M1, is equal to 0.6. It works with the picture that we've drawn here. It's a magnification less than 1. All right, now comes the trick, is we're going to look at the second lens. So I'm going to extend the lens plane for the second lens downwards, and I'm going to sketch the optical axis. And here's my converging lens. And the trick here is to notice that the image, key point, the image from the first lens becomes the object for the second lens. Image of lens 1 becomes object for lens 2. Okay, so now with that information here, I have an object distance, S2, which is 20 centimeters plus that extra 6, 26 centimeters. I have a focal length of 20 centimeters, which is right where, the same location as the diverging lens. It's my focal point on each side. So now let's just draw the principal rays. I have the parallel ray, which goes through the focus point. Right, then I have the ray that goes directly through the center of the lens. And then I have the ray that goes through the near focal point and emerges parallel. And again, this ray, we can see that this is one of the rays for a converging lens just by reversing the arrows. Now they all converge over at this point, over here. So I get an object, or I should say an image, which is real and inverted. S2 prime, real and inverted image, and S2 prime, when we apply the thin lens equation, comes out to 86.7 centimeters. And the magnification is -3.33. Okay, so if I multiply these two together, that actually will give me my total magnification, but let's say that this object originally had a height of 2 centimeters. Well, the final height, we're going to call this H2 prime. What does H2 prime equal? H2 prime equals -4 centimeters. All right, so that takes us then to the end of our discussion regarding lenses. And the purpose of this video is to give you some familiarity with how to start working with lenses. But obviously you'll have to do a number of the calculations on your own in order to get the real practice. But hopefully this answers some of the preliminary questions getting started.